Good day, ladies and gentlemen. We are now looking at our second system, fluid-fluid reactions. Basically, fluid-fluid reactions have a number of applications. These mainly include getting the desired product in the separation point of view. And the typical examples are oxidation, hydrogenation, sulfonation, carbonation, fermentation, polymerization reactions for desired product. And we also have, for the separation point of view, we have wet scrubbing and gas absorption. So the approach for fluid-fluid reactions depends on the following: the overall rate equation, the equilibrium solubility, and the contact system. And in this particular presentations, we'll focus on reactions that follow this kind of equation. A, which is in the gas phase, then gets absorbed in the liquid phase and reacts with B, which is in the liquid phase, to produce a product of any state. The important thing to note here is that the reaction takes place in the liquid phase. There are some terms that you will come across that you need to be familiar with. One of them is a fractional liquid of the reactor, which is FL, which is equal to VL over VR, where VL is the volume of the reactor and VR is the volume of, where VL is the volume of the liquid and VR is the volume of the reactor. And we have fraction of the gas, which will be FG over VR. And we have interfacial area, and the interfacial area also is, one will be interfacial area of liquid. This will be interfacial area, or the surface area available for contact over volume of liquid. Then the usual interfacial area, which will be the gas liquid interfacial area over the volume of the reactor. The first rate equation that you're going to look at is for straight mass transfer. And as shown by the equation, straight mass transfer basically means there is no reaction. We only have A in the gas phase becoming A in the liquid phase. And the diagram summarizes the number of phases that are there. So basically we have the main body of the gas, we have the gas film, we have the liquid film, then we have the bulk liquid side. And there are two resistance here, there's gas film and the liquid film. And these are the equations showing the rate at which A will be transported between these two films. And combining this with the Henry's law equation, this will give us the rate equation for straight mass transfer equation. And that's the equation represented at the bottom. The next set of equations that you're going to be deriving are for reactions that have both mass transfer or straight mass transfer and reaction. And because of different rates at which reactions take place, we have a number of cases, and these cases are divided into 8. And these cases move from very fast reaction that takes place in a plane to a very slow reaction that takes place in the bulk liquid. And these 8 special cases are summarized by this graph. Special case A, basically we have a reaction that's taking place in the liquid film. As we had said earlier, the reaction only takes place in the liquid film. And the reaction takes place in a plane. And as you go down, the reaction becomes slower. It gets to a point where it's taking place in a reaction zone. And it gets to a place where the reaction is taking place not in the film but in the bulk liquid. There is a term called the Hatter number and an enhancement factor. This term will enable us to do calculations and get we have said previously that there are 8 special cases. Using the Hatter number and enhancement factor, we can determine these 8 special cases, and this is based on the overall rate equation. So this is our overall rate equation. It is made of 3 resistance in series. We have the gas film, we have the liquid film, and we have the bulk liquid film. and all the terms in the equation should be familiar except for E. E is called the enhancement factor, and this is the rate of uptake of A when reaction occurs divided by the rate of uptake of A for a straight mass transfer reaction. So basically this tells us that the enhancement factor tells us the extent by which a reaction has been enhanced by a reaction, or absorption has been enhanced by a reaction, or the extent by which the reaction has been improved or absorption has been improved by a reaction. So E is always greater than or equal to 1. And if E is equal to 1, it basically means that the reaction has not enhanced the absorption. And E is dependent on two quantities, the Harter number and the enhancement factor for an infinitely fast reaction. And the definition of Harter number is maximum possible conversion in the liquid film, the maximum diffusion through the liquid. And depending on the value of the Harter number, we can know in which of the 8 cases our reaction is. If MH is less than, or the Harter number is greater than 2, then these become the ABCD cases. If the Harter number is in between 0.02 and 2, this becomes EFG case. And if the Harter number is less than 0.02, this becomes case H. And the Harter number and the instantaneous fast reaction enhancement factor are summarized in this graph. So we have 3 regions. We have this region where the Harter number is less than 1. Basically in this region, this is where we said we have case H, where the reaction has not enhanced the rate of reaction. So basically our E is equal to 1. Then we have other cases. So looking at the bottom, we have a case if EI, or the enhancement factor for an infinitely fast reaction, is less than Harter number divided by 5. In this case, this is how we calculate E. So E becomes equal to EI. And the second region that you have is a case where EI is equal to, is in between, okay, where the Harter number is in between 5 EI and EI divided by 5. And in this case, we determine the enhancement factor from the graph. Then we have the last region, which is on top, where EI is greater than 5 mH. And in this case, our enhancement factor is equal to the Harter number. We did not cover the 8 cases here in detail, but this is important for us to know these 8 cases and visualize what's happening. So now from here on, we will focus on reactor sizing. And there are 2 kinds of contactors, towers and tanks. And these are packed columns, bubble columns, mechanical agitated contactors, spray columns. And these are appropriate for different uses. For a system with a high Harter number, we need a device that can create a large interfacial area, since gas volume is controlling, and also it should have a high gas fractional requirement. And for a system with a lower Harter number, we need a system which has large liquid, because the gas film is controlling, hence a high FL. And other comments are there on the tab. And basically you will notice that for average interfacial area, we have pet bed, template tower, and have stage bubble columns. While it's for very high interfacial area, we have counter current flow, static mixers, and agitated tank and bubble tank. And for a system that has a high FL, we have the tanks, the bubble tank and the agitated tank. While it's for systems which have very high FG, we have spray tower, packed bed, and the blade tower. Now we'll develop the performance equations for different reactors, and these are some of the terms that you will need to, or will be coming across, that you will need to know. T represents total moles in the reaction liquid, whilst Ya is partial pressure of A over partial pressure of inerts. Xa is concentration of A over concentration of inerts, and a molar flow rate of gas and liquid respectively, whilst Fg is upward molar flow rate of inerts in the gas, and Fl is the down molar flow rate of inerts in the liquid. Then we have also these terms where pi is the total partial pressure, Ct is the total concentration, change in Ya is given by that, and which will be equal to total change in the system divided by the partial pressure of inert squared, while it's for a dilute system it will be dPa over Pu. Same thing with dXA, where is the total change of concentration in the system divided by inert concentration squared, while it's for a dilute system it will be change in concentration of A over change over concentration of inerts. The first performance equation that you're going to have is for straight mass transfer tower, straight mass transfer reaction for a plug flow and plug flow gas and plug flow liquid in a countercurrent tower. So we need the material balance. So material balance is as follows: A lost by gas is equal to A engaged by the liquid, which is equal to our rate of reaction times dVr, and that would be that in terms of equations. And equation 3, where now we have Vr is equal to that, and we'll focus on the dilute system, where the dilute system is equal to equation 4. And for the dilute system, if we substitute minus Ra for a straight mass transfer system, we get that equation where those are as given in equation 5. Then the other thing that you will need for our performance equation or for sizing our reactor is material balance, and those are the material balances. The first one is for a case where the system is not dilute, and for the other one is a case where the system is dilute. And the important thing here to note is that we should always arrange Y in minus Y out so that it's positive, and the same thing with the x's. It should be X out minus X in so that it's positive. This is for a countercurrent system. If this was to be co-current, you should still make sure that the right side, the change in Y is positive, and also the change in Y in X is also positive. The second system that you're looking at is mass transfer plus reaction, and we're still doing a countercurrent tower, plug flow gas and plug flow liquid, and that becomes our equation. And as usual, as before, we have our material balance, where A lost by gas is equal to 1 over B lost by liquid, which is equal to rate of reaction times change in volume. And for a dilute system, that will reduce to equation 3. And these are the performance equations for a dilute system and a general system. Those are equations 5 and 6 respectively. And basically what you need here is the area under the integral, and this is shown on the figure. The next system that you're looking at is mixed flow gas and mixed liquid flow in an agitated tank conductor where we have both mass transfer and reaction. Same equation, material balance, A lost by gas is equal to 1 over B lost by liquid, which is equal to the disappearance of A by reaction. And these will be our equations. I think the important thing here to note or to know about the agitated tank is that the conditions in the tank are the same as the out conditions, such that we evaluate our rate of reaction at the exit conditions. And if we do that, then we make the subject of formula, we have the size of our reactor. And the next system we have is a plug flow gas and mixed flow liquid in a bubble tank conductor for a system which has both mass transfer and reaction. And in our last two reactors, I assume that you understand when we integrate and when we don't integrate. We integrate for a system where there's a variation in our properties along the reactor, and this is for columns or towers. While it's for agitated reactors, we don't integrate because the conditions are constant within our reactors. So in this case, we have our material balance. A lost is equal to disappearance of A by reaction. So these are our performance equations, and from the ones we need to solve the integral. But the important thing here to note is that we have the out conditions for SB out, for SB, and those are the conditions that will be used for calculating our minus R. Then the pressure will be varying. That's why you're integrating the pressure from the inlet to the outer. The pressure will be varying. That's why you're integrating it. And these are our design equations or performance equations for this system. And these are our references. So, and I will encourage everyone to understand when we integrate, when we are doing our design, our performance equations, and when we don't, and why. Thank you.